Joseph. That's massive.
That's big.
You have a problem, Dan. What's going to happen for your website?
Yeah, well, I'm not gonna try to compete. That's for sure.
Maybe.
I'll buy you out.
Probably even better.
Bane, so I don't know if you saw that on Slack, but so Rowan works at Sequent, which
Right.
is a company that just acquired Geosoft. And I forget, Dom, I don't know when you did that, but as a joke, is that fair to say? Dom bought geosciences.xyz, just the domain, and it redirects to his GitHub account right now.
But now I'm hoping that they'll keep the name GeoSciences, because otherwise it's worth nothing.
That's true. Right. So if that's the case, you're even better shaped.
Yeah, I'm in great shape.
Excellent. Cool. Well, Bane, I'm really excited to hear about what you have to say today. And I'm excited to see, I mean, I know you've been working on some pull requests and we've been going back and forth a bit.
Yeah.
So extremely excited to get 3D visualization hooked up with discretize. So I will hand you the floor.
Yeah. So yeah, thanks everyone for having me today and for taking the time to check out the pull requests I had going on in discretize. And today I figured I would just share a Jupyter notebook with everyone. So I figured that's sort of the best way to do this. And I guess I should post that Jupyter notebook on the Slack channel so you all have access to it, but I'll also share my screen. Where is this? Just in case it's a bit laggy. So here is the Jupyter notebook. Cool. So the Jupyter notebook is shared in the Slack channel, and I'll go ahead and share my screen with you all, however that happens. Cool. Can you all see my screen?
Yes.
Perfect.
Okay.
Cool. So yeah, so I have this Jupyter notebook put together. Feel free to take a copy yourself and play around with it. Just a disclaimer, this will only work if you have the VTK branch in discretize on your local machine, as well as the master branch of PVGeo. So in this notebook, I'm just going to go over a few things. One, the introduction to PVGeo, just sort of tell you all what it's all about, how we can use PVGeo, and sort of where I hope to go with it. Then I want to focus a bit on that VTK interface in discretize, just run you through how you could use the API of implementing a pull request, and maybe sort of talk about where to go from there. And then focus on what that pull request, what that interface allows us to do in discretize and PVGeo, and sort of how do we pair PVGeo and discretize in a Python environment, and not only PVGeo but also just general VTK algorithms. And then I'll finish it up with just some general examples of how we use PVGeo and ParaView, and what that looks like, and maybe some features in PVGeo that might be of interest to you all working with the SimPEG projects. And of course, feel free to just interrupt me at any time and ask questions if anything comes clear. So keep it casual. So first, PVGeo, it's just a Python package for creating like really compelling and integrated visualizations, both in 3D and 4D. So we do this all in ParaView right now, and the whole library is built upon VTK, which is incredibly scalable and well maintained. And so the whole purpose of why we chose to build everything off of VTK is we didn't really want to reinvent the wheel. Like VTK and ParaView are already these really robust scientific visualization libraries. And so we might as well harness all those common visualization tools for our geoscience data, because our geoscience data isn't really special. It's, it's voxels, it's points, it's all that. So the role that we're trying to have PVGeo fill is just be this link between all of the geoscience and this VTK ParaView realm of data visualization. And so PVGeo allows us to link things like our inverted models, our geophysical data, like the observed data in space, and just other geoscientific information that is spatially referenced. We have all these separate entities in geoscience all the time. We might go from software platform to view them. And what we're trying to do in PVGeo is just find a way to bring all of it together in one rendering environment that is georeferenced. So PVGeo takes all of that and pipelines it all into VTK data structures, into ParaView, and that allows us to take all of our geoscience into new domains, such as VTK.js, which is sort of a JavaScript library for web visualization of VTK data objects and data structures. It allows us to take all of our integrated scenes. So as soon as we have something in ParaView visualized, ParaView allows us to take all of that into virtual reality, which we've been doing a lot of work with here at the School of Mines. And then just other platforms like ParaView Web, the in-situ processing with ParaView Catalyst, and all types of high-performance algorithms that are implemented through the VTK backend. And so it really is just trying to provide this link between geoscience and this really robust visualization and data analysis library. Cool. And the notebook, here's a little abstract with a few links for you all. Feel free to read through that if you will. But this is the abstract for AGU this December. So I'll be at AGU trying to give a nice demo of PVGeo, an overview again. And here's some resources for you all to check out. The demo page just has some, overview, some stats, just a few quick examples about how to use or what can be created with PVGeo. So I hope my stream's not too low for you all. But we have these interactive visualizations, and these are all made using the VTK.js framework.
That's cool.
Yeah, so as soon as we take our visualizations in ParaView, which we made using either filters or file readers in PVGeo, and we have these awesome rendering environments, we can just use an export script to make these little renderings and share it via a web link with just about anyone. And it just proxies a Dropbox URL for the data files.
That's sweet.
Yeah. So the VTK.js is still in its early stages of development. So they create these fairly simple renderings where we don't really have the coordinate system or anything, publication quality. But it's a good way to. The way we use it is we make our renderings real quick and we ping it on Slack over to someone else in our research group. Like, hey, does this look weird to you? Or what's going on here? Check this out. So it's just a good way to share data in a fast, portable way.
That's cool.
Yeah, on the website we have links to the Vimeo channel, which is some general videos on how to use file readers, filters, all that great stuff. So tons of stuff. We have a Slack workspace. Please feel free to join it. We try to keep it, PVGeo users or just anyone using ParaView in the realm of geoscience. Just a place to ask questions and get feedback, share some cool visualizations. The code's all on GitHub. And here's some more links if you want to explore around a bit more. The code docs are on Read the Docs, Vimeo videos, and then the website, pvgeo.org, has a ton of examples about how you could use PVGeo in just a typical Python environment. So you just import our module or our package, and in PVGeo we have all these different suites for different areas of geoscience processing, file I/O, just different sort of domains within geoscience. And then within each suite we have just all types of algorithms that we can call and then apply them on our input data objects. And so this web page runs you through how you could use them in a Python environment, and then really what's important is how we use them in ParaView explicitly. So like this one right here, we just open up the UBC octree mesh format. So Goodney from SimPEG will help me implement this octree reader, and we just hit file open just like that, choose the octree reader, and I cut out a little bit of the lag it took to load the file, but it just constructs a VTK data object in your rendering environment immediately. So just cool videos for you all to check out all over there.
And you mentioned processing. What do you have, or what do you connect to for processing?
At the moment, we're really doing all of that post-processing sort of analysis and trying to keep it all visualization, because that's what we've been able to build up recently. As far as like really trying to do any type of true geophysical processing or anything like an inversion. We just don't have that implemented because we need those direct interfaces back to data like SimPEG rather than trying to build in like true processing algorithms in PVGeo.
Yeah, fair enough. I was thinking that too, because there's packages too, like Fadiando. There's some processing in SimPEG, and we're working on more. So it's a good place to plug in, hopefully.
Yeah, and that's really what I want. Is I want to find a way that we can link ParaView and PVGeo, so that way you're in ParaView and you can have your data sources in the rendering environment, and then go to the filters menu and apply a filter that runs a quick algorithm on your model space to do some sort of processing. And it calls it back to Fadiando or SimPEG, and then the results come back to ParaView, rather than trying to implement all of that in PVGeo or in ParaView. I think it's, it would be really valuable to have that link between all of these software libraries. Cool. So just some takeaways. The presentation will be at AGU.
Are you using the open source software session?
Yes. I think.
Excellent.
Yeah.
Oh. Do you know who's the chair of the session?
Lindsay, you are, right?
Yes, I am. So glad you'll be there.
Yeah. I'm looking forward to it a ton, just get the work out there and meet tons of other people and figure out sort of some other processing libraries or visualization libraries and how we can link it all together. It's going to be exciting.
Excellent.
Yeah, so the other big takeaway we push a lot here is this virtual reality. ParaView has some native VR functionality where you're just in ParaView, you have your rendering environment, and you just click a button that says send to VR, and you put on your VR headset and it's there. So it's been really awesome to take like this whole data scene here and have it at life scale and be able to explore around in virtual reality with other really complicated scenes. And we have some videos of that online on Vimeo, as well as some others we hope to put on the Minds Geophysics website before long for people to check out. Cool. So that's sort of my overview of PVGeo, what we can do with it, why we're doing it, and all that. And I want to move on to talking about the pull request I made in discretize to get the VTK interface between discretized mesh objects, VTK data objects, and sort of just talk about how you could use that in your Python environment.
Bane, just before we kind of get down to like kind of detailed stuff, how it's supposed to use, because it's more like if you have some sort of input file after that, basically we're using ParaView, or you have more interactivity like using some Python script, and then if you run a function, something pops up, or what's the sort of scope of PVGeo? Is that basically you're writing some sort of input file that we can read in the ParaView, or there are more things that we could do?
Well, yeah, so at the moment, it's really all about you have your data, you have it processed, you have your working directory of sort of everything you're running in your processing software, whether that's SimPEG, some commercial software, and you have your intermediate files, your working files. And the whole thing we're focusing right now is let's make PVGeo work for your working data formats. So, so that way you don't have to convert or make output files. You run your software, your inversions, all of that in your working directory. You have your project, and you don't do anything extra really, besides maybe saving out intermediate results that PVGeo can see, it can look at, and immediately render in ParaView. That's what we've been focusing on right now. But there is definitely a way where if you use ParaView's Python interpreter, where you can link up your virtual environments in a way that you can use anything in a normal Python environment you might, such as SimPEG, for your processing, and then use PVGeo and all of the rendering functionality of ParaView to do your processing, and then make a call to visualize that data structure immediately, and have a little window pop up. So there are ways to do that. Right now, we don't have a stable way of doing that in Jupyter notebooks. But that's definitely sort of the next big item on our agenda is, how do we just start making interactive visualizations like this one directly in a Jupyter notebook using PVGeo to make, have your topography surface, your model space, all of that.
Right. Can you go up a little bit? I've just got a little bit of like kind of question there. Okay, so here, let's suppose you got like kind of different data sets. You got a surface data, borehole data and probably some voxel models in 3D.
Yeah.
Yes. And so basically, if like I need some sort of Python array, and then somehow using PVGeo, I'm outputting those file formats as a like ParaView format using PVGeo, and then I'm reading in. Is that what's going to happen if I want to generate that image with the PVGeo? Is that right?
No. I mean, you could do it that way, but that would be a bit cumbersome.
Right.
So the sort of what we want you to do is just if you have, if you have a working data format like the UBC mesh and model formats.
Okay.
I have file readers in PVGeo right now that read that directly, so there won't be any data conversion. But yeah, if you're in a Python environment right now and you're running your inversion and you have sort of your inverted model as a NumPy array in your live environment, you will have to save out that model array to a file format, whether that's your UBC mesh and model format or just anything else. If it's a binary file, we have ways to read in just random formatted binary files and make a data structure out of it. So we're trying to make it as universal as possible.
Okay. Yeah. Okay, that sounds good. Thanks, Bane.
Yeah. Cool. And I'm gonna step into that a bit more after I talk about this discretize VTK mixin. I'm going to talk about sort of now that we have this VTK mixin and in discretize what that enables PVGeo to do. So I'll circle back to that in a minute. So overall, this whole VTK pull request I made, I wanted to implement a way that we could have sort of a direct way to call to VTK, and the mesh will just spit out a VTK data object of your mesh and your models. So in this example, I just create a pretty simple mesh grid, which we just have wireframed here. And then if I wanted to, so after I make this tensor mesh with only a few cells, I can just call this toVTK method on my mesh data object, and that spits out a VTK rectilinear grid. And the way I implemented this is that there's a VTK interface class that only gets imported into discretize if the VTK Python package is available. Otherwise, this function is just simply not available. And it would be available on any mesh object that you have. So tensors, trees, and the curvilinear meshes you just call toVTK. It handles understanding which mesh object you have and then which data structure we need to make. And so just an example here, I call mesh toVTK on my tensor mesh, and it makes a VTK rectilinear grid. The two are pretty much synonymous, so that the VTK rectilinear grid really is just exactly how you all define your tensor mesh, just in the VTK data objects. But I also added in this pull request the ability to define your reference frame. So here I just decide to rotate my reference frame a little bit, just redefine my x-axis direction, my y-axis direction, and same with the z, keep it positive or keep it the same. And then I just validate it, make sure they're all ortho, whatever the word is.
You have no idea how many times we use that.
Yeah. So yeah, and so I rotated my tensor mesh now, and so everything on the back end side of discretize right now remains the same. We just have this reference frame we can use if we need it, and the toVTK functions use it. And so now when I call mesh toVTK on my tensor mesh object, it sees, hey, that's a rotated mesh. Let's not use a VTK rectilinear grid because that doesn't make sense in VTK. Let's use a VTK structured grid, and this would be the difference between the two. So this green one here, where it's parallel with the traditional axis in a Cartesian space, is this green mesh, and then the rotated one where I redefine the axis directions is the same mesh, just rotated in space. So
Is there also the ability to like shift your x naught, for example?
Yes, so I was thinking about whether or not I should do that. And because there's the x naught, the origin property of all the meshes, and so we should probably use that. And so I just figured maybe there would be a good way to just put in a Boolean on your 2V of whether or not you want it rotated and how you want it rotated.
That's fair. Yeah.
Yeah, because all it would be is just a little bit more matrix math on the rotation. That wouldn't be hard to implement. So yeah, so now we have this really simple API for creating these VTK data objects. So we could use this in PVGeo, we could use it in other VTK-powered Python environments. And so if you have, your VTK rendering scripts for just a standard Python environment, then all you would have to do is just call this to VTK and pass that data object on. And so now I want to talk about, now that we have this, how does PVGeo use that?
Bane, I was like, after that, I do mesh.vtk. If I want to load it up, that mesh in the ParaView, what do I need to do?
So yeah, so that's what I'm gonna do here. So I'm gonna run through a quick example I'll just jump ahead. Okay. So with this to VTK interface in discretize directly, what I've done in ParaView is made it so if you have your mesh saved as either the JSON format or the UBC mesh and model format, then we can use then we can use a plugin I've made in PVGeo it calls discretize, and it says, okay, I have a file name I want to use. Let's use discretize all of their file IO for this format because it's their format. I load it in as their data object. So discretize, this is a tensor mesh object when it's loaded, but PVGeo is sort of indifferent about what that data object is, and then we just pass that object onto this get VTK data object function, and PVGeo just handles the rest. And so this passes on my discretize mesh as a VTK data object, which enables me to use ParaView to just hit file open, and then you just navigate to where you have your UBC mesh format, and you hit OK. And I just select, let's use that UBC tensor mesh reader. And I can also choose model files if I need to. So we have that OPOP. And it just loads in your mesh just like that.
Oh, I see. I'm a little bit confused because it seems like you got a mesh and model as a file.
Mm-hmm.
And then you're basically loading up and in ParaView. That's what's happening. And why do I need to? I wasn't sure what's actually happening actually when you're doing mesh.vtk. Is that actually writing the files, or it seems like you're generating an object?
Yes.
I wasn't sure where it seems like at the end of the day you're writing some sort of files.
Right. So I already had those files saved on my device. So right here, when I call mesh.choosevtk, I create that VTK data object in my rendering environment. So if I just assign that object, then I can make calls on it like it's a live object in my environment. So this is the VTK data structure with all of its stuff going on. Or we could write out those VTK data formats by mesh.write VTK, which is also implemented in that pull request. But I just don't really see a need to use that. I think it's better to use your UBC format, your working processing formats, rather than these static copies of a VTK format. Because then you get sort of messy with having random versions or static versions of data that isn't up to date with your processing routine. So
jump in with following up on that a bit. So in a simple sense, like if we're running through a very SimPEG driven inversion, then doing like mesh.save and then saving your model as a NumPy array, that's enough for PVGeo to ingest that mesh and model. Is that correct?
Absolutely.
Does that make sense, Sergey?
So the reason why I'm a little bit confused, because it seems like, okay, I got a Python array, so that's my output, okay?
Yeah.
I got a mesh model.
Yeah.
And it seems like I need to somehow output that to read it in ParaView. Or is that like there's an object, so that somehow is that connected to ParaView, so I don't really need to kind of like upload or like output the files? That's something that I'm
So you saved the mesh as a JSON and you saved your NumPy array, right?
right.
And so then those two things, PVGeo can ingest a discretized mesh and model and turn it into a VTK styled object.
Right.
So you don't actually have to, correct me if I'm wrong on this, Bane, but we don't actually have to create a VTK file.
Oh, I see. I see.
Yeah.
That's a correct interpretation?
Absolutely.
Excellent.
Definitely right. Like these VTK files, I put these in here just because they're easy and just because we should have them. But you definitely don't need to use them, and I wouldn't recommend it. I think you should keep your data in your data format for the things that are most convenient to you and to your processing routine.
So Bane, now you generate the object of like VTK object by doing mesh.toVTK. Then, like, can I see that in ParaView now? Is that so it's connected?
No. So these environments are not connected. These are standalone environments right now. And so what I wanted to demonstrate as well is, okay, now in discretize, you have this toVTK method that spits out a VTK data object at you.
Yep.
How can we use that in a Python environment? So I put this example together from an example data set found on the SimPEG website, where it just already had some discretized meshes and all of that, and a topography surface. And so I wanted to run through this example where I load in my mesh. You can create this in your Python environment however you want to make your mesh. And then we have this live mesh object from discretize. There is also a process model I include just because they give us a little bit of visualization to see what's going on. And I want to run through this example of, okay, now I have my mesh. I have, say, a topography file as well, which is this file right here. In my working environment. So let's just say all I have is my model space, which maybe I'm tweaking and trying to design to make it better. And I have my topography surface. And so what can you do in a Python environment to play around with that? What I've done is I've created this little example where we read in our topography file, which just has XYZ values. And in PVGeo, we have a special reader for certain topography formats that make this VTK polydata object immediately. So just one line of code right here to just read in that topography data. I have my VTK polydata. And then let's say I want to use that topography information, which is right here above my service, and I have my model space, which maybe that model space goes above the topography. Let's then create a way, let's create an active cell array of whether or not any given cell in that mesh is above or below the topography surface, and then we can spit that right back out into Python or into NumPy arrays to use. And so that's what I do here. I just call PVGeo in this grid suite. There's an extract topography filter, and I take that mesh.toVTK. So I get that VTK object of your mesh from discretize, and I pass that topography file. That topography file is just straight from data file. And I just run this algorithm. So now I have another VTK data object here that just contains all that information about whether or not the cells are above or below the topography. And I can use PVGeo to interface that VTK data array back over to NumPy. And so now I just grab that active topography array, add it to my models dictionary, and then use the new plot 3D slicer to just plot that active cell array. And so here we see there's my topography line, and here's the top-down view of the valley. And so it's just a quick way to run any PVGeo or even a VTK algorithm, get the results over PVGeo's VTK interface, and use it again in your discretized code. And so this is a really simple example, and I think you all have some functionality in SimPEG or discretize to do this kind of thing. But I don't want you to focus so much on, it's only used for extracting topography. The whole point is that now that we have this mesh.toVTK method, we can interface the discretize code with the PVGeo code so that they can talk to each other and share the results. So PVGeo gives us this active topography array or maybe something else, and we can use that in discretize immediately. And so this doesn't only hold for PVGeo. I was like, we could also use this for VTK algorithms. So just using the VTK Python suite, Here's a really simple filter, the cell size filter.
All right.
And so as soon as I have my VTK algorithm, I just set in my input data object as the mesh VTK object, straight from discretize, update my algorithm, get the output, use PVGeo on the interface, and there it is. They're sharing the results, talking to each other.
Nice. Okay, that's cool.
That's really cool.
That's crazy. Huh. Yeah, so we can actually use all the VTK functions and.
Yeah.
You remember, Sag? We're depending on one to decide what cells is inside or outside closed surfaces or above and below. It's all depending on VTK, right? So we can interact with it directly now.
Right. That's cool. So cool.
Yeah, and so I'm super excited about this, and I want to simplify this whole process here of making these VTK algorithms. So you have to instantiate them, set your inputs, set your parameters, and then update it. And I've been thinking about, it would be really cool to create sort of another library that sort of interfaces with VTK, so you don't have to do all 5 of these steps, but maybe just call cell size filter, pass in my VTK data object, and it just spits out this NumPy array at you.
Yeah.
So I think there's a ton of potential in how we can take this, how we can simplify it, how we can use it, interface all these different libraries together.
That'll be.
That's really exciting, and that also then trims down, like from our side, the number of utilities and things like that that we need to maintain.
Yeah, that's
so
great.
things like topography right now, we've got a whole slew of utilities for that, but it would be so nice to just rely on VTK for that. Wow, cool.
That's cool. Yeah. Well, the bottleneck, what we were thinking about using VTK, but it seems like, I don't know, that kind of the protocol and how they're using the code wasn't just unfamiliar.
Yeah.
But I think now it's actually like, it's much better. I think I can still use it. So
yeah.
Great.
Yeah. There's definitely a learning curve on the VTK code, and but once you get it, the Python package is super easy to use. And with PVGeo, we can create all these interfaces. And I've only really just started getting started with these interfaces like PVGeo.getArray.
Yeah.
So I'm just hoping I can build out a lot more of these interfaces to make it so PVGeo can help discretize or help SimPEG communicate with all the VTK processing or all the PVGeo processing or other filters and types of stuff. So I think that's most exciting thing here, how we can bring together all these libraries. And just sort of to wrap everything up, there on the website there is tons of examples, which I'm trying to fill out as best I can. But I just put a few here that might be interesting to you all for sort of the data types and structures you're working with. So in PVGeo, I just made this UBC suite. Has file I/O for the tensor meshes, tree meshes, as well as for model data that might be time varying. This allows you just, if you have all of your UBC files already saved out, you just hit File Open in ParaView, and you can make these really integrated visualizations, along with other information. So maybe you have other geospatial information given to you in some other data format. PVGeo or ParaView can read that in and just put it in your rendering environment right alongside all of your working data formats.
So Bane, I actually got a question. So to generate that plot in ParaView, you need like quite a bit of work, right? You need to add the slides and then add the surface and then assign the color, change the color scale. Can you actually set that up in the script? Is that possible?
Yeah, so that is possible. We can't do it in a Jupyter Notebook.
Oh, cool. Oh, cool. That's so cool.
Yeah, so we can't do it in Jupyter Notebook right now until someone or we make some sort of library for that. But if you use the PV Python, it's a Python interpreter that comes packaged with this GUI application. So if you go to the application contents, whenever you download ParaView, there's a little executable called PV Python, and it allows you to use all of the rendering functionality in ParaView in a Python environment. So I can set the color map, I can I can say, hey, apply a slice here, and just automate these functions. And you could use PVGeo directly in that Python environment to automate any of the filters we have for creating different types of slices and all types of stuff.
So that's a ParaView function, right? It's not. Is that PVGeo or ParaView?
So the Python environment's definitely ParaView.
So a couple things to mention. I don't know if you know, but I'm going to be moving to Berkeley very soon, like 2 weeks. But I'm going to be working with the Jupyter team.
Okay.
And so I would be extremely keen to work with you on how to get this working in a Jupyter notebook, or perhaps, and probably more likely, within Jupyter Lab.
Yeah.
So let's keep in touch on that, and just like keep that on your radar that I will be there and excited to make this happen.
Yeah.
Yeah, and then I wanted to just get your thoughts and sort of trajectory on the Python 2.7 to Python 3 migration with ParaView, and because I'm just sort of out of the loop on how that's happening and what the timelines are for that.
So your question was, SimPEG and discretize, you're trying to go into Python 3 only, drop support for Python 2.7, and you're curious sort of what I would need on the PVGeo and ParaView side.
Yeah, and then also just like what the timelines are, because we don't actually have to rush to get off of Python 2.7, and if there's lots that we can continue to take advantage of, then that might sort of change our timelines as well.
I don't have a solid timeline off the top of my head for when ParaView is going to drop 2.7 support. I think it's scheduled for their next major release, which would be at the end of the summer, I think.
Okay.
That's the time frame I have in mind, but I could double check and try to keep up on that. But I know, like, within the ParaView community, there's a whole bunch of people that are just begging for it, and so it's going to happen. But might be a while.
Yeah, and VTK, does VTK work in Python 3?
Yes. Oh yeah.
Yeah.
So it's definitely more stable in Python 3.
Yeah.
Yeah. But ParaView, unfortunately, when you're using everything in ParaView, it's got to be 2.7.
Okay. Fair enough.
I see.
Cool.
So just like a kind of writing the files, and like if I have a Python array and write the file and then read it in ParaView, like using Python 3, there's no problem.
Right.
And then there's different types of data, like a surface data or point data, and like borehole data. Like the PVGeo has all functionality that I can write out as a VTK file format. Is that correct?
Yeah. So so if you have all of your your borehole data, say in like the open mining format.
Right.
I've been working a bit, and it's not on the master branch, but like you can read in the open mining format, get your borehole data, visualize in ParaView, and you can either save it back to the OMF format, or you could save it to a VTK format or something else.
Okay.
So, yeah.
Okay. That's cool.
Yeah, so what do you need from us on the discretize side of things? I've seen a few questions coming in on your pull request. Are there things specifically you would like to chat through while we're all live?
I don't have too much questions. I guess the main thing, and I was thinking about the other day, is whether or not we should rotate around the origin, and that's pretty simple when we do those rotation things. The thing that I tried to play around with was getting the rotation code within the grid code. So when you call grid nodes, whether or not it rotates it or not, I had some trouble with that. I didn't know where everything was making calls to. That might be something really simple for someone else familiar with the grid code to implement.
Okay.
I figured that would be a cool way to, or a good way to just sort of keep it all universal.
So the idea being like, taking an edge grid and rotating it?
Sure. Yeah.
Okay.
Because all of these XYZ points, right?
Yes. Yeah.
Yeah. So if they're just XYZ points, you just use numpy.dot to dot your matrix with of your points with your rotation vector from axis UVW.
Right.
So it's super simple, and then just gotta add in that rotation on the origin. Just because otherwise we have all those properties, the axis UV and W, that only the VTK interfaces using. So.
Right. Yeah. Yeah. So right now, like all of the grids are just properties.
Mm-hmm.
We would have to. I think we have to think through if we want to rotate the grids or not. Oh, that might work because we're not actually calling.
Or just make a new property called rotated grid.
Yeah, that might be easier. That might be easier. Okay, well, we'll think through that and sketch something up.
Yeah, so that stuff, and I ran into a ton of validation issues.
Okay.
Meshes, which I put a little issue on discretize, but it was something back in the, I think in the C++ code for the tree mesh that I just got lost in. So
that's fair.
Yeah. Yeah, so I think it looks good. Just definitely check it out, whoever's interested, and leave some comments and some feedback if something doesn't look right.
Yeah, certainly will do. Do you guys have other questions? No? I'm just sort of curious, what are other projects that you are interfacing to, or like, are there other open source projects that you're reaching out to, trying to tie in? Yeah, I don't know.
Yeah, I'm super eager to. So I'm excited about the AGU open source session to figure out some more people who would be interested in collaborating.
Yeah.
Right now, I put together like a few really lightweight, small packages like off to the side for reading Landsat imagery.
Mm-hmm.
So I implemented this Python package where we can just read in Landsat imagery straight off of Earth Explorer, which is the US's Geological Survey's data portal.
Yeah.
That data, and then this Python package I made just reads in those formats, creates a nice object to hold all of your metadata with your Landsat imagery and the image. And then I created a little interface for PVGeo to just make calls back to that an interface. So I haven't really done this with anyone else's projects, really. It's kind of just been side things for me when I need to visualize data for a project I'm working on here at school.
Yeah.
Right now, it's all just been, what do I need, or what does my research group need?
Yeah.
And that's pretty much where it's gone. And I've been swamped, so it's been hard to collaborate with anyone outside.
Yeah, fair enough. Well, we're also hosting a town hall at the AGU on open source software. I think it's Tuesday or Wednesday night. I can send you the details. But if it works for you to be there, I would really appreciate getting your perspective on things and your input, because it's going to be fairly open-ended, but the goal is to try and figure out, like, if we have a giant body like the AGU that is supportive of open source, like, what should it be doing? And so, yeah, I think it'll be an interesting conversation, and hopefully, well, I know there'll be quite enough number of other sort of developers that are big in the open geoscience Python community.
Yeah.
So I'll be sure we'll make some connections and do all that then too. So it'll be good.
Yeah, I look forward to it. And thanks again for having me today and for checking out PVGeo, taking the time to ask questions and learn some more about what's possible. Look forward to seeing where it goes.
Yeah, for sure, man. We will push some questions to you later.
Awesome.
Absolutely. Well, thanks, Bane. Much appreciated.
Great job. It was great.
Thank you.
Cool. All right. Well, we will be in touch, and I'm extremely excited to see what we can do together. So it'll be fun.
Have a good day, everyone.
See you guys.
Bye-bye.